firstly, we're going to go through the two worksheets that you did last week. Both of these are to do with the electrolysis of molten ionic compounds. So when you're doing this, it's quite abstract on paper, but you should in your mind have this picture, okay? And you would have seen the video that I sent of the electrolysis of a molten ionic compound, so you can have that in your mind as well. But you need to remember that we have this electric circuit, we have two electrodes, and then we have the molten ionic compound here. And remember, there's only positive and negative ions in here. There's no water in here. So what you've taken is you've taken a salt, like the salt in your cupboard, and you've melted it down so it's a liquid. And then the negative ions are attracted to the positive electrode, and the positive ions are attracted to the negative electrode. All right, so that's the idea that we're thinking about while we're doing these questions. So I did a few of them last week, so I'll just carry on here. So we've got the bromide ions. Okay, they're going to make bromine. So in order to do that, they're going to go from a negative ion to a neutral molecule. So they're going to have to lose electrons. All right. So we're going to lose electrons like that. However, it needs to be balanced. So this needs to be 2 there and a 2 there. Okay. And this here, remember, this is a covalently bonded molecule. Okay, and it's bromine gas. So if you did this in an experiment, you would see bromine gas coming off orangey brown gas. Okay, now let's do this one. So calcium is a group 2 metal. All right. So in order to go from a positive ion to the neutral atom, we're going to need to gain electrons. How many electrons do we need to gain? Well, if it's a 2+ ion, it needs to gain 2 electrons, and then it's going to form Ca. Now, is that balanced? Yes, it is balanced. I've got 1 calcium here, it's an ion, and I've got 1 calcium here, it's an atom. So the calciums are balanced. Are the charges balanced? Well, I've got a 2+ ion here, and I've got 2 negative electrons, so yes, it does balance. Okay, and you should be thinking, when you look at this, that what you're really doing is, you're taking the ion that's in the ionic compound, and you're forming back the metal. All right, so this would be the ion from your salt that would be dissolved in water, but you get back your metal. All right, and so here we've got loss of electrons, gain of electrons. This is loss, this is gain. So if this is loss, it's oxidation, and if this is gain, it is reduction. Okay, and last one. So we're going to go from O to minus to O2. Well, if I've got 2 oxygen atoms here, I'm going to have 2 of my oxygen ions here. And then to go from negative to neutral, I'm going to need to lose electrons. So I add my electrons over here. How many electrons do I have? Well, each oxygen ion is 2-, and I've got 2 of them. So I'm going to have to lose 4 electrons. All right. So down here, if the ions are Cu2+ and Cl-, in order for that to balance to a neutral compound, it's going to be CuCl2. So then I do at the negative electrode, that's going to be my positive ion, so it'll be Cu2+ plus 2E- goes to form Cu. Okay. Now when I was doing this, when I was going through some of your answers, I did notice that some people were maybe putting a 2 here and then a 2 here. All right, which isn't right. Okay, so if you were to write something like Cu2, okay, remember copper's a metal. If you write a 2 down here, you're sort of saying that this is going to be a copper molecule, like this. All right, now we know that that can't be right because copper isn't covalently bonded. Copper is metallically bonded. So you can't have this picture. This picture is wrong. And this formula is wrong. All right, remember copper is a metal. So it's made up of lots of copper ions, like this, in a regular lattice, all right, with the C of delocalized electrons, all right, and what that means is because it's only got copper in it, the empirical formula is just Cu because there's only one type of atom in it. So it's just copper metal. All right. So the product is copper metal, and then the positive electrode is going to be your negative ion, so it's going to be Cl minus, makes chlorine gas, and then you balance it the same way. Now I do have Cl2 because chlorine is in group 7, it's a non-metal, so now I can have a chlorine molecule, so that is a thing. All right, now it's chlorine gas, and these molecules will float around. The bond between the chlorine atoms is very strong. The bond between chlorine molecules and other chlorine molecules, this bond here, is very weak, which is why it's got a low boiling point. All right, so the product there is Cl2. All right, and then the next two are just the same, like that. So you'll notice that the only interesting things here are that because the charges on these are the same, the formula is ZNO, it's a 1-to-1 ratio, whereas this one it's 2 and 1, so it's going to be CaF2 again. And remember that all of the metals, the formula is just the metal. Okay, there's no number after the metal or anything like that. And for group 7 elements, so bromine, chlorine and fluorine, those are all diatomic, so it's all Br2, Cl2, F2, and oxygen is also diatomic. Right, and I mean these equations here, these will always be the same. They will always look like this. Okay, so fluoride ions, chloride ions, they won't do anything different. They'll always do that. They'll always lose electrons to form these, and metals will always gain electrons to form the metal. Metal ions will always gain electrons to form the metal. All right, so let's go on. Magnesium chloride contains Mg2 plus Cl minus. Which ions attract to the positive electrode? So it's going to be the Cl minus. Why? Opposite charges attract. And what is made at the positive electrode? Well, at the positive electrode, just like we had up here, all right, we're going to make our chlorine gas. So Cl2 gas, all right, and we'll do that in the lab, and the whole lab will start to smell like a swimming pool because chlorine is what they put in swimming pools to kill bacteria. All right, write a half equation for the process at the positive electrode. Like I said, it's always the same. So it's going to be Cl minus is going to lose electrons to form chlorine gas. However, every chlorine molecule has 2 chlorine atoms, so I need 2 chloride ions, and I lose 2 electrons. Does oxidation or reduction take place? Well, it is the loss of electrons, so it is oxidation, okay? And the explanation is electrons are lost. All right, and then the second half is the same, but with the metal, like so. And the last question is the cathode positive? Is the cathode the positive or the negative electrode? So I remember panic. So positive anode, negative is cathode. So it is the negative electrode. Okay. We go on to the next one. All right. So up here, by now, you should be getting the hang of these half equations. Okay, so the only one here that's slightly different is this one, where we have H+. Now, remember, hydrogen obviously is not a metal, but you see that it is being reduced like a metal. So the hydrogen ions gain electrons to form hydrogen molecules in the same way that a metal does. All right, and that'll become important when we do the electrolysis of solutions later on. All right, but all the other ones, they're all just your normal. If it's a non-metal, they lose electrons in oxidation, and if it's a metal, they gain electrons in reduction. Okay, and then for these ones, so the only difficult thing here is to make sure that you're getting these formulas right. If this is a 3 plus and a 2 minus, it must be Fe2O3, NaI, nice and easy, and this one's going to be NiCl2, and then the equations will be, so those are your equations. All right, again, notice the pattern. At the negative electrode, so at the cathode, it's always going to be reduction, the gain of electrons, and you're always forming a metal. So calcium, iron, sodium, nickel, those are all your metals. And then at the positive electrode, at the anode, it's always oxidation, so you're always losing electrons. And so you get your non-metal, all right? Because metals. Metal ions gain electrons, non-metal ions lose electrons, okay? And so almost always at the positive electrode, you're going to get a gas released. And that's because, think about it, these are non-metals. Non-metals are covalently bonded. Molecules that are covalently bonded have weak interactions between the molecules. Therefore, they have low boiling points. Therefore, they are gases. All right, so it all connects back. All right, so the product from the electrolysis, you can link it back to your structure and your bonding that we learnt about. Okay, so this is a useful process because we can get the metal from the ionic compound. So one area where we do actually use this in industry is in the extraction of aluminium. All right, this is a really, really important process for us to be able to get aluminium from aluminium oxide. All right, so what we do is we dig up the ore from the ground, and so it's not just aluminium metal that you dig up out of the ground. You dig up this rock. Inside the rock there is aluminium oxide. We need to get the aluminium from the aluminium oxide, and we use this process of electrolysis in order to be able to do that. Okay, and there's a few extra details that we don't need to worry about too much at the moment. But you know, as long as you read this, you can get a good idea of what's going on. So explain why aluminium oxide does not conduct electricity as a solid. Okay, so that is because in a solid, remember, it's an ionic solid, so the ions are in a fixed position, which means that there are no free moving charged particles to carry the electrical current. Okay, so no free moving charged particles to carry electrical current. Okay, so if in here you said anything about delocalized electrons, that's wrong, because delocalized electrons is to do with metals. I know that we're thinking about aluminium, but we're thinking about aluminium oxide. So even though aluminium is a metal, aluminium oxide is an ionic compound. There's no delocalized electrons. It's all to do with the positive and the negative charges being able to move. Okay, so if you melt it down in here, you do now have free moving aluminium ions and oxygen ions that can carry the charge. All right, and then we know that we've got the aluminium ion and the oxide ion, so filling out this table should be fairly straightforward. So there are your answers. And the final question, which is a little bit extra on the end, why is a molten mixture of aluminium oxide and cryolite rather than just molten aluminium oxide? Okay, and the reason is, so if you read this bit up here, okay, if we mix it with cryolite, it melts at a much lower temperature. Okay, so if you think about it, we want aluminium, but if we have to heat up the aluminium oxide to 2000 degrees C, all right, our electricity bill is going to be really high, which means that the price of aluminium is going to be even higher. Okay, so yeah, aluminium's good, but if it's too expensive, then we're not going to use it. So anything we can do to make the production of aluminium cheaper is going to be good for the cost of aluminium. So we use aluminium in all kinds of things, and one of the reasons is because we're able to reduce this cost by lowering the temperature it needs to be melted at from 2000 down to 950. All right, so it is to lower the melting point. All right, which saves us money.